Being an astronomer is one of those days where you can have days that are quite relaxed, where it's just me and my computer working away on some simulations, or you can have days where you are entirely nocturnal, up on an observatory, looking at beautiful views of the stars while you are, taking observational data, or other days where you are going to fantastic places and traveling the world to talk science to some pretty amazing people. So yeah, it's a really cool career.
Normally I spend a disproportionate amount of time on my computer. Sometimes I spend some time thinking about cool theories. Often I'm looking at data from satellites or from ground-based telescopes, trying to understand how it all fits together and paints a bigger picture of black holes and how we want to understand them. If I want to study X-rays coming from black holes or neutron stars which are being fed by material, I might use XMM Newton, which is run by the European Space Agency. I might use Chandra or NuSTAR, which are NASA satellites. If I want to go to different wavelengths, maybe I'll use the Hubble Space Telescope, maybe I'll use James Webb, or maybe something on the ground, you never know, like the Very Large Telescope, or I might use radio arrays like the Very Large Array in New Mexico. Lots and lots of different stuff. I'm really interested in black holes and how space-time is bent and shaped around them. I think these are really, really exciting questions that touch on fundamental physics. Obviously, I'm very interested in finding the hidden black holes in the Milky Way galaxy. And for that, we're using instruments that normally look in the optical bands, so TESS at the minute. So we predict there should be all these hidden black holes in our galaxy, and I want to find them. Because that's really exciting, like where are they? And if they aren't there, why aren't they there? And if they're there in more numbers than we expect, what does that mean for our understanding of physics and things like the evolutions of stars?
How do we make a black hole? Black holes are the end stage of the stellar life cycle, so how stars die. So stars are held up by radiation pressure, which is what is created when they burn hydrogen and helium. That energy pushes outwards against the gravitational force pushing it in. But eventually, they run out of fuel.
You can no longer extract any energy from it. So the core starts to collapse, and it does so very quickly. The physics are unclear exactly what happens next. We know that a huge amount of energy is lost via neutrinos, and those neutrinos can actually unbind the star, so they're a really important element of that. And then something happens, and we're left with something left, right? Something that's very compact, and that could be a neutron star, where you have weird phases of matter, really strange stuff going on. Or you could have a black hole, which some might argue is weirder still. And so that's how we think we form these black holes. At least these are the small ones. You can form much bigger black holes called supermassive black holes in the centers of galaxies.
One thing that is fascinating to me is that this energy release, we also see it in the environment. When you look at the pictures of these systems, especially in the optical and radio bands, you can really see how the energy has been imprinted into the interstellar medium. So one thing that I try to do is to, by measuring how much energy has been channeled into the interstellar medium, try to quantify how these systems, through this accretion process, affect their environment and whether they can even have an impact on the whole galaxy, for instance.
At the moment, I'm working on a project called Black Hole Hunters, where we've got a ton of data from a satellite called TESS, and we're looking for particular shapes in what are called light curves. So a light curve is like a graph that shows how bright a star is over time. So we've got lots of repeated measurements of each star showing how bright they were hour by hour, minute by minute. And we're looking for sudden changes in brightness.
When you have stars that are together, they tend to interact, or they can certainly interact through various different coupled means. One will age faster than the other. The massive one ages faster, it burns through its fuel faster. So that's going to become a neutron star or a black hole. And then there's a supernova explosion. That supernova explosion can unbind the binary, so it can kick its star away from it, in which case, that's it. I mean, with a free-floating neutron star or a black hole that's wandering through the galaxy. If the supernova is not that strong, then they can remain coupled together. And those are the systems that we'll be able to find. So by finding them and understanding their numbers and their characteristics, we can start to understand how do supernovae really work.
So one theory or explanation is that you have this binary system, which may not be, mass transfer may not be occurring at all. suddenly the star will enter a new phase of its evolution, either maybe because it has fused the hydrogen in the core, or and then we know certain stars like the Sun, for instance, inflate. While before it was compact enough for the material not to fall into the black hole, as it expands, it feels the gravity from the black hole much more. It can start to channel the mass onto the black hole.
When we make our predictions, we are reliant on theory, and we develop our theory or we should develop our theory in consultation with reality. So occasionally we have to go, well, this is how a star should evolve, this is how plasma physics should behave. Let's just check that that's actually what we're seeing. And then what we essentially do is say, let's create a galaxy on our computer, let's fill it full of stars and binary systems, let's watch them evolve. And then we're going to work out how many have black holes, how many have neutron stars, what are the properties of these binaries, their periods, so their orbital period, the relative masses, all these other things. If you do it enough times, you get to explore all the different evolutionary pathways sufficiently that you can have a reasonable guess at how many systems there should be. But that is entirely predicated on our belief in the theory that underpins it all. If that's wrong, which it might be, then we have to revisit our expectations. But by doing this project, by trying to find lensing black holes, it gives us an opportunity to test our understanding. What we will be provided with by finding these black holes is a window into how supernovae occur. This is something that we can't really penetrate. A supernova occurs so quickly that there's no indicator really on the outside of the star until the envelope of the star gets basically kicked away. We don't know what's happening in the core. And so what we're going to do are find these hidden black holes, because actually they're going to be essentially unchanged since they formed. They've just been going round and round with a friendly neighbour star. Okay, nothing else has really changed about them. So if we can find them and study them, we can start to understand supernova physics. And that's going to be really exciting because there's no other way to really probe that.
There are things that are really easy for a person to spot that are basically impossible for a computer to find, or at least impossible for it to find reliably. So that's why we need help from the public. That's why we need volunteers, because we need people to look at every single graph to make sure that we don't miss anything. And there's just more than we can look at ourselves. So having help from the public is hugely important to us.